And one of the things I did want to do is walk through this a little bit. And it sounds like all I did was a very little bit. There's a piece I'd like you to see, only because I think it's nice that you guys know things. And I'm often trying to help you guys appreciate that knowing things has value. Most people don't recognize that your automobile does something rather miraculous, and it's something that I even indicate in this discussion is something that was being researched quite heavily by like people like Napoleon and stuff way early to try and find a way to harness this idea. You might not know exactly how this works by the time we're done, and that's fine. I don't care if you know exactly how it works. I think it's interesting that you know part of how it works. Your car engine is a heat engine. And if you don't know what the word engine really means, it means to change. It's not the thing you think it is. Engines change things. A heat engine changes heat into motion. Most engines do create motion. But a heat engine exchanges heat for motion. Steam engines, gasoline engines, they're all heat engines. And you might wonder, well, how do you exchange heat for motion? Now, the truth of the matter is, trying to make an efficient heat engine is not easy. And although we have done an incredible job, I say we, I mean we as humanity, have done an incredible job making engines more efficient, they are not very efficient at all. When you think of the grand scheme of efficiency, they are terribly inefficient. Now, if you guys don't understand exactly what efficiency means, that's fine. But even a really efficient car doesn't actually fit the definition of being efficient. Most of the energy is wasted. And the energy is exhausted to the environment in the form of heat that can't be used for anything. Only a small percentage of the actual energy gets utilized by the vehicle. The other thing that's impossible for you guys to know at this point in your life is that there are no systems that are 100% efficient. The research done by Carnot, which was funded by Napoleon, was able to finally show that there's a limit to the level of efficiency of any system, and it's limited by the temperatures in which it operates. Those limits can't be violated, which means that no matter how efficient your system is, it will never be as efficient as a Carnot system. And that system, being the most efficient ever, still is limited by the temperatures in which it operates. 100% efficiency requires operation of an engine at either 0 Kelvin or infinitely hot temperatures, one or the other. Since those can't be achieved, no system will ever be 100% efficient. Now, you can do 100% exchange from one type of mechanical energy to another, but efficiency isn't about exchange. It's about conversion. So, a simple heat engine is your car's internal combustion engine. And to say simple really is derogatory for all the things that happens inside your car. Now, for just the simplistic view, one of your car's cylinders looks something like this. So if you have a 4-cylinder car or a 6-cylinder car, you have multiples of these. Most of you guys drive cars that are between 4 or 6 cylinders. A few of you have 3-cylinder cars. A few of you have 8-cylinder cars. You probably know which one of these is yours. But what's important to understand is that all internal combustion engines must work this way. Now, your car is what's called a 4-stroke engine. Your lawnmower, which works in a similar fashion, is what's called a 2-stroke engine. They do operate a little different. So I'm talking about the way a 4-stroke engine works, because that's what your cars do. Now, the cylinder has a sealed side. This area is sealed from the outside. The bottom actually connects by gears and such, eventually to the wheels of your car to make it go forward. Everything below the cylinder is a bunch of simple machines. They convert the type of energy we have from the cylinder into something that will make the car go forward. So there's gears and wheels and levers and such. Now here's the way it works. There is a valve on one side and a valve on the other. Your cars might have multiple valves, but let's just assume that one side of the cylinder is intake and one side of the cylinder is exhaust. And although I'm going to kind of blow through a lot of the details here, the way your car operates is it opens up the intake valve first. Now, lots of things have to happen for gasoline and air to be intaked into your car, into the cylinder. Generally, it happens because of a vacuum created by this piston being forced downwards by the motion of the rest of the engine. But I'm going to skip over that portion because it's not necessary for our discussion. But generally, the intake valve opens first, and that lets in a mixture of gasoline and air into the engine. Now, that mixture is something that, believe it or not, you control with your gas pedal, as you probably imagine. But your gas pedal doesn't determine how much gas goes into your car. Your gas pedal determines how much air goes into your car. Your gas pedal opens up an air valve, which allows more air to come through the engine, and in bringing in air, gasoline is also brought in. Now, at this point in time, most of us drive fuel-injected cars, which means that the gas is injected directly into the cylinder and mixed with the air in the cylinder. Older cars were aspirated using a carburetor, where the gas and air was mixed in the carburetor, and then that was inserted into the engine. Either way, this only works if the gasoline is mixed with the air. That's an important detail because gasoline itself isn't explosive. It can be caught on fire, but it's not an explosive. We want to explode it. We want to be as efficient as possible and get it to burn all the gasoline as fast as possible. So we mix the gas with the air and bring it into the chamber. Then we close the intake valve. It's at this point that the spark plug initiates a small spark which will explode the gas and air in the engine. This explosion will create a temperature in the engine that is many times the ambient temperature of the air. Now, this is kind of funny if you think about this all the way through. Right now, outside, it's about 80 degrees out. When this explodes in your car engine, it's probably going to be around 900 to 1,000 degrees. But your car never gets above 200 degrees, which means the entire time your car is operating, it's containing this explosion, but doing everything it can to make that explosion happen so fast that the car engine doesn't heat up past about 200 degrees. Now, we'll cycle water through your engine to help it cool, but your car engine stays around 200 the whole time. If it ever actually got to the temperature of the explosion that was in there, it would seize up and melt your engine, because the steel melts well below the 1,000 degrees of this explosion. But it happens really fast. And now, this is where PV equals nRT comes into this whole thing. In your engine, T goes up dramatically, maybe as much or more than 10 times where it was. Now, you can't get away from PV equals nRT. If the right side of this equation goes up, the left side of this equation also has to go up, the same amount. So if the right side just got 10 times bigger, the left side gets 10 times bigger. And the left side gets bigger with the pressure increasing first. The air got really, really hot, and because of that, the pressure of that air, pressure is the force of the molecules against their container, increased dramatically. Now, inside this container, the only place that force is effective is on the top of that piston. We don't want the rest of the chamber to expand. So the rest of the chamber stays in place, but there is a huge pressure on that piston. Now, that pressure is going to turn into a change in volume as the piston is forced downwards. So the actual amount of energy that you get here is the pressure times the change in volume. Now, if you don't see it, that's a heat engine right there. It took heat and turned it into motion. And then we focused that motion in the direction we wanted to use it. The reason this is called a four-stroke engine is that after the piston is pushed down, the exhaust valve opens, and because of the action of some other thing in your car, another piston firing somewhere else, this piston will be forced back up to push all of that garbage out of your car so that it can bring in new gasoline in the next round. So the results of that explosion is to take all the byproducts of that explosion and just put them out your tailpipe, which is what you're venting into the atmosphere every time your car cycles one piston. It's not very much gasoline every time, but you guys who have filled your car up understand that over time it builds up. So all of the gasoline that you bring into that car will eventually be burnt in the open atmosphere. Now, luckily, you probably have a catalytic converter and a muffler. Those two things actually collect a lot of the solid particles that are left over from this explosion and will eventually have to be emptied and refit. So eventually you have to replace catalytic converters. You have to replace mufflers because they get full. But a lot of the gas is vented out into our environment. We do actually bring some of that gas back around. Some of you guys know a little bit about cars, know that you have what's called an exhaust gas recycler, which means we reburn some of this to try and get more of the particulate matter out. But there's no way around it. Although it's a great heat engine and we do a lot to make it efficient, we are burning all of that gasoline in the open atmosphere. That's really what's happening. Just because it's nice and convenient inside your car, you should never forget that eventually this leads to a tube that just opens up to the atmosphere. Right? Now, I want to point out that you learn this in chemistry. You never realized it, but it's the whole reason your car operates. So I wanted to give you an appreciation for that, but I also want you to understand something here. The basic part where work is being done, the word work is a specific word we're going to use in this class. And there's a couple ways that this word has to be defined. The first is the work is the method by which you can change something's energy. Work is the method by which you can change something's energy. There's a couple different ways to actually calculate work. Two of them in physics. The one you need to know is this one. Now, this is not force times distance. It's a little more complicated than that because everything in physics is always a little more complicated than that. So, for a moment, I want to really focus on this and just this. This is not multiplication in a traditional sense. It's supposed to be a bigger than life-size dot there, not the little dot you've been using in algebra. This is called the dot product, also called the scalar product. You see, at issue here is the fact that displacement and force are both vectors. And because they're both vectors, you can't just multiply vectors together like you do other numbers. Vectors have direction, and that direction information is important and affects the product. There are two kinds of vector products out there. This is one of them, called the scalar product. And I think the reason it's called the scalar product is going to be obvious. Work is a scalar. When I pause like that, you guys understand that I expect those three words to make it into the old notes. Which means work doesn't have direction. It can be positive or negative, but it doesn't have direction. Positive work increases an object's energy. Negative work takes it away. Again, work doesn't have direction, but positive work would increase something's energy, while negative work would take that energy away. An object cannot have negative energy, not in a traditional sense. And if you remember, we only talked about one form of visible energy, kinetic energy. We talked about that on Friday. So generally, work is a way that you can change something's kinetic energy. And the way you would know that is by seeing if its motion changes. Now, to understand the dot product, you have to understand that there's something very kind of critical here. The dot product means the force that is in the direction of the displacement. That's what that dot product really means. It means to multiply the force that's in the direction of the displacement with the displacement. Multiply the force that is in the direction of the displacement with the value of the displacement. That's not particularly easy to understand without a good visual. So here's a mediocre visual. Remember all those times we were pulling on wagons earlier in the year? So imagine I am pulling with 150 newtons of force on a 10 kilogram wagon at an angle of, say, 30 degrees. Now, I think it doesn't take much to realize that it's likely that the wagon will move. In fact, I think all of us can probably admit the wagon will probably roll along the ground. Let's say that the wagon rolls 5 meters along the ground. The dot product says that work is done when a force is used to move an object. The amount of work that's done is the dot product between the force and the displacement. If we look at this picture, it should be clear that only a portion of that 150 newtons is in the direction of motion. The other portion of that 150 newtons is upwards and is not contributing to moving the wagon. So those of you who are sharp and have been with me through this are seeing exactly what I'm going to say and know exactly what I'm going to write, is that the dot product requires that I take and use the angle that's between the force and the displacement. It tells me how much of the force is in the direction of the displacement. And based on which side of that triangle it is, it's going to be the cosine of that angle. Technically, in a dot product, you take the first vector and the second vector, you multiply them together, and then you multiply by the cosine of the angle between. This is the way the dot product tends to be written in most equation sheets. So our definition of work will look like that. Force times displacement times the cosine of the angle between them. But it really means, with heavy emphasis on knowing this for the test, the force in the direction of the displacement. Now, as a first example, we should take a moment and just calculate how much work is done over here. There's not a whole lot going on here for this example, but please take a minute, calculate it out. You'll need your calculators for it. It's not a whole bunch. It's 150 newtons times 5 meters times the cosine of 30 degrees. Now, I can get to 750, sure, but I need you guys to multiply the 0.866 times the 750 to get me the answer there. So 600 and what? 649? So 649 joules of work was done on the wagon. Now, the next couple things I'm going to say really need to be internalized. They're not obvious. First, how do we know if this work effectively changed the energy of the wagon? What's something that we could see? Yes, sir?
It's positive.
We do know that it's positive, but what effect would it have to have on the wagon for us to know if the wagon gained energy? Daniel?
It moves.
That's right. and not just moved. It has to be moving when we're done. We know that kinetic energy is the outward way in which we see energy. The most obvious way that this work changed the energy of the wagon is that the wagon now has kinetic energy. But be careful. I don't necessarily know if the wagon has now increased its energy or not. All I know is that one force did this work on the wagon. Are there other forces acting on the wagon? Name another force that is likely acting on the wagon. There's definitely normal force, sure. Friction, sure. Anything else? Gravity, sure. These are all other forces that act on the wagon. We found the work done by a single force. That doesn't mean that that's how much the energy of the object changed. This statement probably is the most important statement of the day, so please make sure you keep it in mind. That the net work done on an object, the net work done on an object determines how much the object's energy changes. The net work determines how much the object's energy changes. Individual forces can do work, but the net work determines if the object's energy changed. Just because you gave an object energy doesn't mean that the object's energy changed. Look, you guys drag these chairs all over the room. When you're done dragging them and let go, do they keep going? Where'd the energy go? I mean, if you gave the chair energy, clearly something took it away. If you don't understand what the connection is here, look at these three forces acting on the wagon. Two of them can't do work on the wagon. Which two, in this instance, can't do work on the wagon? Normal, sure. Look at the normal is pulling upwards or pushing upwards on the wagon. Is it in the direction of motion? So it's not doing work in this instance. How about the weight? Weight's downwards. The wagon's moving to the right. Is the downward force in the direction of motion? How about friction? Friction's harder. To really see friction, you have to really pay attention here. Clearly, the wagon moves this direction. Right, that's the direction of motion of the wagon. That would be the displacement. What is the angle between the displacement and the friction? From here all the way to here. How many degrees? What is the cosine of 180 degrees? Glad that unit circle's working out for you. Cosine of 180 is -1. Do you understand the importance of that statement? That means friction does work on the wagon. By definition, in this case, friction will do negative work on the wagon. It would have to. Friction would always do negative work because it's always against the direction of motion. Friction would always do negative work because it's always against the direction of motion. That means if you drag that chair across the room and you give it 300 joules of energy, it is likely that friction took away 300 joules of energy. And when you're done, the net work on your system is 0. Chair's not moving. It's important to note that the object only retains its energy if, when you are done, there's a positive increase in the total energy. If the net work is positive, then the energy stays with the object. By the way, the net work is the sum of the work done by every individual force acting on the object. The net work is the sum of every individual force acting on the object. All right, let's flip to a new slide here. And for the time being, I'm really only talking to the the really mathy people, because I think you'll appreciate this. All of you need to know the result of this. But you guys who have a good appreciation for math, or if in the future you'd like to be able to tell other people what to do for a living, pay attention to this. Because people who know why things work tend to have people who just know how they work to work for them. You ever heard that phrase before? People who know how things work will almost always work for people who know why. It's just the way things work out in nature. So understanding why is important here. Newton's second law looks like this. We know that. If there's an unbalanced force, then we know that the system's going to accelerate. I'm bringing it up specifically because of our definition of net work. Net work is going to be the net force times delta x times the cosine. Since the definition of net work is the sum of the work done by every force, this would be the way of expressing it. Does that make sense to all of you? Now, for just a few moments, let's assume that the net force is in the direction of motion, either speeding up the object or slowing it down, but it's not causing the object to turn. That way, I can use this substitution and not have to worry about the centripetal force. Does that make sense? So I'm going to make that substitution, and I get ma times delta x. You might not know the answer to this, but we have seen a delta x before. It's appeared in one of your motion equations. If you look back at your motion equations, you have v final squared minus v initial squared equals 2a delta x. Look familiar? I could clearly do a little bit of substitution here, as it's always nicer to work with velocities than accelerations. So I'm going to substitute, and I'll get that net work equals m times 1/2 v final squared minus v initial squared. You guys see that okay? I'm going to distribute. When I distribute, I get 1/2 m v final squared minus 1/2 m v initial squared. What's this? What am I calculating when I do 1/2 mv squared? Yeah, that means this is the change in kinetic energy. Net work causes a change in kinetic energy. This is called the work energy theorem. And it's exactly what I said at the beginning of this. If you wish to change something's energy, then work is the method to do so. By the way, since you all have to run out, take just one moment and look at the similarity here. Don't they look similar? It's not accidental. Impulse and net work have a lot of similarities. We tend to use impulse when time is very small, and we tend to use work when delta x is large. We'll talk more about this tomorrow.